Alright, thanks for watching, and let me ask you a question. What is infinity minus infinity? If your answer is 0, then this video is for you because today is all about indeterminate forms, which is a cautionary tale about the fact that infinity does not obey the same algebraic laws as real numbers do. And by the way, in fact, this is why we have calculus, really to show us that we have to be a little bit more careful. Infinity minus infinity isn't always 0. In fact, I want to illustrate that it can be whatever we want. So, indeed, let me illustrate a scenario where infinity minus infinity is infinity. So let's calculate limit x as x goes to infinity of x squared minus x. And by the way, today's video is not about limit laws. I will not show you how to calculate x squared minus x. I just want to introduce indeterminate forms and in fact illustrate that in indeterminate forms there is a tug-of-war going on between two quantities. So, now let me give you an analogy for this. Suppose you have some money which you put in a bank. So if x is 10, what this means is you have $100, you put it in a bank, and the bank charges you a certain fee. Let's say $10. Then what you have left is $90, which is a moderate amount of wealth. But suppose now you start with $10,000 and the bank charges you $100. Then what you have left is $9,900, which you see is a much bigger number. So, I mean, you're losing some money, but not that much. And lastly, suppose, even better, you invest or you put $1 million in, and the bank charges you $1,000. Then doesn't look that big anymore, right? Then what you're left with is still a big amount of money, $999,000. Okay. What is going on? Notice, the initial wealth that you have is actually getting bigger and bigger. And in fact, as x goes to infinity, this quantity goes to infinity. Okay? So x squared goes to infinity. On the other hand, the fee that the bank charges you doesn't look that big, but notice, in fact, it is getting bigger and bigger, just a bit more slowly. So the bank fee also goes to infinity. So we have infinity minus infinity, and the question is, what is that? Well, notice the difference is your net wealth. And your net wealth is actually going to infinity as well. So indeed, in this case, in this particular scenario, we get infinity minus infinity equals infinity. Now, the question is this a general law? And in fact, I want to show you no. And this is why you shouldn't just naively play with infinities. Consider now the following scenario. This time you put X amount of money in your bank and the bank charges you a fee of $8. Then what you have left is $2. And indeed, what I'm illustrating here is the limit as x goes to infinity of x minus 2. So 10 minus 2 is 8, so it charges you $8. Now, let's say you have $100. Then the bank charges you $98, and you have $2 left. And if you have $1,000, the bank charges you $998, and you still have $2 left. My suggestion, please switch banks, because this is kind of horrible. But the whole point is, in this scenario, your wealth, initial wealth, goes to infinity. So we have infinity. But the bank fees also goes to infinity. But in this case, the two things are comparable, and we get, in the end, the answer is always 2. So even in the long run, your net wealth will be 2. So in this case, infinity minus infinity is 2. So what do we have? So the question is, what is the answer? What is infinity minus infinity? Is it 0, what you probably suspected? Is it infinity, in the first example? Or is it 2? Or could it be whatever, something else? In fact, the answer is we don't know. It's what's called an indeterminate form. Just if I give you infinity minus infinity, just those two things, the answer is we don't know. We need more information. You see, we need to know precisely how big this infinity is and how big this infinity is to figure out what the answer is. And if you want formally, the definition is, if the answer is any value, from minus infinity to infinity included, then it's what's called an indeterminate form. So it depends on the scenarios, but basically if there is, it can really take on any value that it wants, then it's an indeterminate form. And again, today's goal is not to go into the limit laws, but to really go over all the indeterminate forms and also illustrate, again, that there's a tug-of-war going on between those two quantities. So, this is one example of an indeterminate form, and now let me give you another example. One of my favorite ones, infinity over infinity. And let me illustrate this with the following simple limit. Limit x goes to infinity of x squared over x. Now, suppose that in this world there are two YouTube channels, Dr. Peyam and Black Pen, Red Pen. And suppose we live a long and happy life, and more importantly, an infinite life. Then, the question is, how successful will our channels be? So, here's the thing. Black Pen, Red Pen is awesome, and he will always be. And I totally believe that, he really deserves it, right? And basically, he will always be more awesome than me. And the question is, how much more awesome? Well, assume squared as awesome as me. So, which means that if I have 10 subscribers, he has 100 subscribers. If I have 100 subscribers, he'll have 10,000 subscribers. If I have 1,000,000 subscribers, if I have 1,000 subscribers, he will have 1,000,000 subscribers. So notice, I'm not saying I'm pairing badly, right? My subscribers increase, and eventually they will go to infinity. But what I'm saying is, Black Pen, Red Pens will go to infinity faster, like x squared, whereas me is x. And the question is, how much more popular will Black Pen, Red Pen be compared to me? So, by the way, again, this is really infinity over infinity, because we'll both get infinitely many subscribers. And here's the thing, initially, Black Pen, Red Pen is 10 times as popular as me. Then, he is 100 times as popular as me, and then 1,000 times. So the question is, how much more popular will he be? Well, the answer is actually infinitely more popular. So, this is the case where infinity over infinity is actually infinity. And that's because, notice, there is this tug-of-war going on between the numerator and the denominator they both go to infinity, but because this one goes way faster to infinity than the other one, because Black Pen Red Pen is so much more popular than me, his popularity, the ratio of the two, goes to infinity. Okay, so this is one of them. Another one that's related, it's 0 over 0, and again, for similar reasons, it depends on how fast the 0 is. And then one that's also very neat, which is 0 times infinity. And in fact, it's neat because it is exactly the same as this one. So it becomes 1 over infinity. Like this thing, you can write this as 1 over infinity times infinity, which is 0 times infinity. So, in fact, they're the same quantity, and because, again, 2 is indeterminate, this is also an indeterminate form. And again, why? Because it could take on any value possible. And in fact, let me illustrate this with an example as well. Suppose you're in a country, and you're the king of a country that has infinitely many people. And you have to collect taxes, and suppose you're a nice king, you say, I only collect very little tax from you, like a negligible amount. Think a breadcrumb from a bread. And the question is, what is the total tax collected? Well, the answer is it depends. It depends on how many people there are. If there are if there are really a lot of people, like x squared amount of people compared to, let's say, 1 over x, then this goes to infinity. If those are comparable in some sense, then the answer could be 1 or 2 or anything. But on the other hand, if you really collect so little taxes that it's truly negligible, then this might be 0. So, for instance, suppose, again, there are infinitely many people, or like, let's say, infinitely many infinitely many people, but your tax is really as small as 1 over x squared, then it turns out that's just the limit as x goes to infinity of 1 over x, which is 0. So in this case it's 0, it could be infinity, it could be any value. This is why it's indeterminate, and again, that's because of the tug-of-war going on between the two quantities. Okay, and before I move on with power laws, I want to give you some example of determined forms, so not indeterminate ones. One of the famous ones is 1 over infinity. And let me ask you this. Suppose you have one cake that you distribute among infinitely many people. How much cake does everyone get? Well, probably nothing. Not even a crumb, because there's so many people and just one cake. So, sorry, no cake for you. And this is not indeterminate. This is, no matter what this infinity is, no matter what this 1 is, it's 0. And indeed, notice here there is no tug-of-war going on. Infinity is a large number, and then 1, well, it just stays 1. And 1 over a big number, there's no debate. It's always 0. In particular, there is, it cannot take on any value it wants. It only takes on one value. And similarly, there's 0 over infinity. Again, no tug-of-war going on at all. This is, is a large number. This is nothing. Nothing over a large number is also 0. Okay, on the other hand, there's one thing I have to say, it also surprised me, which is 1 over 0. And that was interesting because it does take on many values, but it's not indeterminate. And at least according to Wikipedia, Because look, if we have 1 over a very small value, 1 over 0 is 1 over 0.001, well, that is 1,000, which is big. So it could definitely be infinity. That's what I'm saying. Think, limit as x goes to 0 plus of 1 over x. Similarly, it could be minus infinity if you just replace this with minus. 1 over a small number negative, that's minus 1,000, which you can model as being minus infinity. And also, one cautionary thing, right? Don't always think limits exist. It could also happen that limits don't exist, like think this thing here. Limit x goes to 0 plus, and then 1 over x sine of 1 over x. And let me just illustrate what is happening. You see, basically, this function x sine of 1 over x, by the squeeze theorem, which we might learn later, this x sine of 1 over x, it goes to 0, but it oscillates. So it kind of oscillates between 0 plus and 0 minus. So 1 over that goes to either plus or minus infinity, and it really can't make up its mind. It looks something like that. You see, it gets bigger and bigger, but it cannot make up its mind. So it could also not exist. So don't always think limits exist. It could also not exist. But it turns out this is not indeterminate because it only takes on 3 values. It only takes on a couple of values. In particular, it doesn't take on any value. You see, for infinity minus infinity, it could really take on a whole range of values, but here, not really the case. And there's not really, think of it, there's not really a tug-of-war going on. This 1 is stay just 1, and then 0, well, it's just 0 plus or minus, one of the two things, and there's kind of no debate going on. It's probably some form of infinity. Okay, and now, that was all the ratio thingies going on, and now let's move on to some power laws and some indeterminate forms with that. So rule number 5, it's infinity to the 0. And this I found very interesting because, again, there is this conflict going on between the base and the exponent. So consider the following. Square root of 2, okay, which is roughly 1.41. And now consider doing 2 separate things to this number. On the one hand, let's just increase the base. So then we get square root of 3, which is roughly, I believe, 1.73. Let me double check. Yes. And then there's square root of 4, which I know how to do without the calculator. That's 2. And so in particular, notice what is happening. If we increase the base, then that thing goes to infinity, right? And this is sort of what this infinity wants to do. It wants things to go to infinity. On the other hand, notice square root of 2 is 2 to the 1/2. And now, let's deal with the exponent. Let's make that exponent go to 0. Then, we have cube root of 2, which is roughly 1.25. And then the 4th root of 2, which is roughly a 1.90. So you see, we have that the exponent, what it wants to do, it wants to put that number closer and closer to 1. Notice those numbers are getting closer and closer to 1. So there is actually this big debate going on. Because on the one hand, the base wants things to blow up to infinity. The exponent wants things to go to 0. And then there is this tug-of-war going on, and the answer is, we don't know. It depends on what our function is and how this pair is relative to each other. For instance, you can show that the limit as x goes to infinity of x to the 1 over x, this goes to infinity, this goes to 0, you can actually show that it's 1. But you can modify the exponent base and the exponent to actually make this go to 0, to infinity, to whatever you want. And similarly, there is 0 to the 0, where we have the same tug-of-war, because the base wants things to go to 0, the exponent wants things to go to 1. So you see, we don't know what the answer is, because it really, again, depends on the relative quantities. That said, be just careful. 0 to the 1, that is not an indeterminate form, because the base wants things to go to 0, the exponent wants you to do nothing, right? 2 to the 1 is 2, 3 to the 1 is 3. So really, basically what happens if those two were in a battle, the 0 would win, because 0 to anything is actually 0, except if the exponent is 0. So what I'm saying is here there is no debate, it is not an indeterminate form, and similarly, actually with 1 to the 0, because 1 to the 0, the base wants you to go to 1, the exponent also wants you to go to 1. So there is an agreement here, so it's also not an indeterminate form. This is just 1. On the other hand, last but not least, is I think the most interesting example, which is 1 to the infinity, which is indeterminate, because look, this wants you to go to some number, and I'll explain this, and this wants you to go to 1, but here's the problem. Maybe there's no tug-of-war, but it's very unstable. Because look, if this number is slightly bigger than 1, think 1.002 or something, and you raise this to the infinite power, then this actually goes to infinity. Because think 2 times 2 times 2 times 2 times 2, etc., this goes to infinity. On the other hand, if this is slightly less than 1, 0.998, and you raise it to the infinite power, it actually goes to 0. Because think, for example, 1/2 times 1/2 times 1/2 times 1/2, eventually it becomes 1 over 2 to the infinity, which is 0. So, because we don't know precisely what this value is, right, then we can't really say what the limit is. And we have to use calculus to figure out exactly what the limit is. And indeed, let me illustrate with this very famous limit, 1 plus 1 over x to the x. Notice, this goes to 1, this is infinity, so it's 1 to the infinity. And what's interesting is, this is slightly bigger than 1, so you might think that it's infinity, but it's not quite true, because this goes to 0 fast enough compared to the exponent. The answer is actually, believe it or not, e. Who would have thought? Some number that's bigger than 1, but not quite infinity. And in fact, I think it should make sense that the answer is not 1, because if you remember from pre-calculus, this has to do with continuous compounding. So suppose you have a bank that gives you some interest rate, and that calculates that interest rate infinitely many times, continuously. Well, if it's a good bank, or if it's a good savings account, you should eventually get more money than you started with. So this multiplier should be strictly bigger than 1. Which is why it's good that it's strictly greater than 1, but interestingly it's not infinity. Which means which makes sense because otherwise you would be infinitely many rich if every bank did that, so it's not a good investment strategy. And this is, if you want, the last one of our indeterminate forms. So what's the main takeaway from today is, first of all, that in calculus you have to be very careful, right? You can't just naively plug in numbers, say infinity minus infinity, it's 0. So it's kind of a cautionary tale, and also very important that for indeterminate forms, there is some kind of tug-of-war going on, where the answer depends on exactly how big or one quantity is compared to the other, which again justifies why we need calculus to really analyze those quantities more precisely. Alright, I hope you like this. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.